Hola, bienvenido a la última sección. Okay, I'll stop doing that now. Welcome to the final section of videos. We're going to talk about ideal and real gases, mixtures, and reactions involving gases, things like that. We are going to be building on the work we did in the last section, the previous section, I should say, where we talked about the various gas laws, and this time we are going to start with the ideal gas law, or ideal gas equation. So here is where we're going to talk about the ideal gas equation. I'll explain the weird exclamation up at the top in a bit. I'm also going to explain all of these symbols and weird math and stuff. The fact is that it's not that easy to, do math in a PDF slide, but I'm going to take advantage of the magic of Microsoft Paint to go ahead and explain these for you. So, recall that volume is proportional to temperature. Now, what that means is that increasing one causes an increase in the other, or they're linked in that way. That funny fishy-looking symbol means proportional, but you can restate it as V is equal to a constant multiplied by T. Okay, just some constant of proportionality. Okay, that maintains the ratio between them. It's the conversion factor, you might say. That's where we got that V over T is equal to K, and then V1 over T1 equals V2 over T2 because they're both equal to K. They're both equal to that constant, whatever that constant is. But what we need to focus on is V equals KT, because you can get that same sort of mathematical equation for other combinations of constants, such as P equals KT, or P equals K over V, or V equals Kn, right? These are different Ks, obviously. That's what those little slash marks up there are. They mean K prime, K double prime, K triple prime. That's one of the ways mathematicians use to keep their various variables distinct. It's just, there's only 26 letters, But let's go ahead and do this same thing for the combined gas law. We didn't really look at any sort of derivation for that, but let's just go ahead and take the combined gas law as we know it and go in the reverse direction. P1 over P1V1 over N1T1 equals P2V2 over N2T2. Those are equal to some constant. So now you just say P1V1 over N1T1 equals K, and you rearrange and you get PV equals KNT. This is sort of the form of the ideal gas law. We're not quite there because we don't know what that constant is. Knowing what that constant is would do us a world of good. Now, we call that constant the universal gas constant. It's universal in that it applies to any gas, and it relates the values of pressure, volume, temperature, and moles for those any gases. Okay? And the symbol we use for it is not K, but R. There is almost certainly a reason for that, but I have no idea what it is. Now, there are multiple values of R based upon the units that you're using for your gas. They look very, very different, but in a way, they're all exactly the same number. Like think about your car. Your car has a certain fuel efficiency. And if you express that in miles per gallon, you're going to get a different number than if you express it in kilometers per liter. But it's still the same fuel efficiency, just different units and numbers. Okay? In a way, it's the same quantity. You're just looking at it from a different perspective. So another way to put it, 1 kilometer, or let's see, 1 mile is 1.6 kilometers. Okay? It's the same distance regardless. So when we look at the universal gas constant, these are all different ways of expressing it. Okay? The most common one is up here at the top. It's 0.08206 liter atmospheres per mole Kelvin. Then we have, just in case, 62.26 liter torr per mole Kelvin. Remember, torr is equal to millimeters of mercury, named after the Italian Torricelli. So that's the same number would be if you were using millimeters of mercury, 62.26 millimeter mercury per mole Kelvin. And then the third one is one that will show up fairly frequently in the second semester, 8.314 joules per mole Kelvin. Because it turns out that the liter atmosphere, volume times pressure, is a unit of energy, sort of. When you expand, when your piston is expanding, it's exerting a pressure across that volume. So it's related to doing work. That's one way to think of it. But this 8.314 joules per mole Kelvin shows up in other situations, other scenarios, when you're, say, working with batteries and so on. So the first one shows up a lot. The third one, not so much now, but more later if you continue studying chemistry. But when you write it all out, when you use the new constant, you can write it as PV equals nRT. Why nRT? Probably because it's in alphabetical order that way, but also because it lets you say PVNERT, which is stupid and dorky, but I love it. So you're going to be hearing it a lot, PVNERT, and you're going to have to get used to saying it as well, PVNERT. And that's why I had PVNERT written on the previous slide. But PVNERT, or the universal, or the ideal gas equation, is something that is kind of ridiculously useful and incredibly common. Now, let's go ahead and work through a few, maybe just one or two examples of what sort of math you can expect to do with the ideal gas equation. Here is an example of a nice and simple problem that you might expect to see. If you have, let's say, a 575 milliliter sample of gas at 375 Kelvin and 2.35 atmospheres, how many moles of gas do we have? So we just go ahead and write out PVNERT, PV equals nRT. Well, it's a 575 milliliter sample, so we have volume, at 375 Kelvin, so we have temperature, and 2.35 atmospheres, so we have pressure, and we'll always have R, the universal gas constant. You can't not have that. So all that's left is in the number of moles. That's what we're looking for. Good. I gave you a problem that can be solved. So now let's just go ahead and do a little bit of that simple algebra we all love so much. Rearrange to solve for n, and we get n equals PV over RT. And then we just plug our numbers into that equation. 2.35 atmospheres times 0.575 liters. Never, ever, ever forget to check your units. Always check your units. Got to make sure that the units match. Liter atmospheres per mole Kelvin in the universal gas constant, so you're going to have to convert from milliliters to liters. Then we have 375 Kelvin and 0.08206 liter atmosphere per mole Kelvin. All right. Now, atmospheres on the top, atmospheres on the bottom, those cancel. Liters on the top, liters on the bottom, those cancel. Then, going down to the bottom, we have Kelvin down there in the bottom. Then we have Kelvin on the bottom of the bottom, so those cancel. And all that's left is moles. Moles are on the bottom of the bottom. That means we bring them up top. Dividing by 1/2 is the same as multiplying by 2. Dividing by 1 over moles is the same as multiplying by moles. All right, so moles come up top. And once you plug those into your handy-dandy calculator, you get 0.0439 moles. Does that number make sense? Well, remember that 1 mole of gas at room temperature, actually at freezing at 0 degrees Celsius, or 273 Kelvin, is going to take up 22.4 liters of space. So if you have a really small volume at high pressure and it's above boiling, Yeah, it's only going to take a very small quantity of gas to do that. A very small quantity, about 1/20th of a mole. So yes, that's a long way of saying this number does make sense. Okay, now let's go on to a slightly more complicated problem, why don't we?
Oh no, Herr Dr. Professor, crankshaft. Your dirigible has been punctured. Okay, I'm going to have to stop with the accent. Okay, so you're flying a dirigible, and it has been punctured by a bullet shot fired by the evil Count Cocoa Puffs. And it's leaking at 0.00825 atmospheres per second. Fortunately, you have 5,000 kilograms of helium on storage on board the dirigible, and you're traveling at a speed of 75 kilometers per hour, and you are 305 kilometers from Leipzig, and it's 0 degrees Celsius outside, and the volume of the dirigible is 4,250 liters. Will you make it to Leipzig, Herr Dr. Professor? That's the basic setup of our problem. Now, I know that it looks really, really nasty awful, but I promise you it is only partly that awful. We can work through it. It's actually surprisingly not terrible. I've thrown a lot of information in here, but this is a PVNERT problem. In fact, we are looking for pressure because the dirigible is leaking. It's losing pressure, and we have helium available to make up for that lack of pressure. Okay? So that's what we're looking for. We just need to find a way to get from the information we have to the amount of pressure that we're losing and the amount of pressure available. So let's take a look at what we got. Now, let's get some of this information out of the way first. We have a speed, how fast the dirigible is traveling at. A dirigible is a balloon. It's a zeppelin, a blimp. Yeah. Those are all slightly different names for slightly different things, whatever. We have the speed it's traveling at. We have the distance that it needs to go to get to Leipzig. So let's just go ahead and find out how much time that will take. 305 kilometers divided by the speed it's traveling at, or multiplied by 1 over the speed. So that's 305 kilometers divided by 75 kilometers per hour is going to get us 4.07 hours. Let's go ahead and remember our sig figs there. And then we will move on to how much, well, first we'll also be recording up in the upper right here how much time it's going to take, 4.07 hours, and then we'll find out how much pressure are we going to lose over those 4.7 hours. We are losing 0.00825 atmospheres of pressure per second, and we have 4.07 hours. Time on the top, time on the bottom, we multiply by hours. It doesn't quite work. We need to convert from hours to seconds. Straightforward enough. 60 minutes per hour, 60 seconds per minute. The minutes cancel, bottom and top. Hours cancel, bottom and top. Finally, seconds cancel, bottom and top, leaving us with atmospheres. So 0.00825 atmospheres per second times 4.07 hours times 60 minutes per hour times 60 seconds per minute gets us a total, remember your sig figs, of 121 atmospheres. And we'll go ahead and record that up top and ask our next question. What is the total volume or pressure available from the helium we have on board our dirigible? Well, first things first, we can't do much with kilograms. I mean, well, we can do a lot with kilograms. We just can't do math with kilograms. Well, we can. We're going to have to. In fact, we're going to have to convert from kilograms to grams because I don't know the molar mass of helium in kilograms. So we convert from kilograms to grams by multiplying 5,000 kilograms by 1,000 grams per kilogram. And that gets us 5.000 times 10 to the 6th grams of helium. And then we go ahead and convert from grams to moles using the molar mass of helium. 5.000 times 10 to the 6th grams of helium times 1 mole of helium per 4.003 grams. That's the same thing as dividing by the molar mass, 4.003 grams per mole. And grams cancel, leaving us with 1.249 times 10 to the 6th moles of helium. And let's go ahead and record that up here next to temperature. And with moles in hand, we can finally move on to asking what is the pressure that this amount of helium will provide. And we finally get to use PEVNERT. And we're going to have to rearrange PEVNERT so that we have P all by itself. That means dividing both sides by V. We get P equals nRT over V. And when we go ahead and plug our numbers in, we've got N is 1.249 times 10 to the 6th moles of helium, times R, the universal gas constant, 0.08206 liter atmosphere per mole Kelvin, times 273 Kelvin. Do not forget to convert. Okay, I give it to you in Celsius, but it needs to be in Kelvin. When it comes to temperature for this sort of thing, it needs to be in absolute terms, the absolute temperature, not temperature relative to the freezing point of water. And then you divide by 4,250 liters, that being the volume inside the dirigible. And that gives us a pressure of 6,583 atmospheres, which is a heck of a lot more than the 121 atmospheres that we're going to lose over the 4 hours and a bit that it's going to take to get to Leipzig. So, will Herr Dr. Professor Crankshaft make it to Leipzig? The answer is no, because he does not know how to drive a dirigible. He cannot get there if he does not know how to drive. He will get lost. He will end up in Munich. Could be worse. Could end up in Bavaria. And that's our second problem. And with that, we're a few minutes over the 15-minute limit I usually set for these lectures, so we will return to talking about the ideal gas law and the sorts of things you can do with it in Lecture 13. See you in a bit.